Hi, I'm Emmett Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Tim Schneider of Arteris. We're going to talk today about the promises and pitfalls of SoC restructuring. Tim, we've got a lot going on these days when we start getting into the complex SoCs. You've got teams that are working on all sorts of really complicated architectures or using methodologies from the past. How are they able to keep pace with those methodologies and tools and what has to happen today?
Teams today, I kind of see them as, they have this side job as data wranglers. They've got to pull data from IP providers. They've got to take requirements from their hardware software guys, and they've got to take, system architectures, meld all these things together, and then in the end, generate a chip. So in this day and age, there's a lot of things on folks' plate, not just, coding the RTL and getting the design out the door. There's lots of other factors that feed into that.
And this gets a lot harder as we get into heterogeneous designs, right? Particularly at the most advanced nodes, because you've got all sorts of physical effects. You've got potentially chiplets that come out of multiple different vendors, and you've got all sorts of timing issues that are going on across a chip as well.
And that is true 100%, Ed, because now these IPs are coming in and they be different formats. Like internally, they may have to pull in system Verilog. Externally, they'll get IP exact, say, from a vendor. Now, how do you meld those two into something? And then how do you go about restructuring when you do have different data that you have to aggregate? And one of the things we've seen at Arteris is there is a common thread with exchange of information, and that is IP exact.
Let's take a closer look.
Sure.
Tim, what are we looking at here?
The definition of a processor is changing, right? With the advent of AI, large language models, with GPUs, CPUs, NPUs, any type of three-letter acronym can become a processor these days. Also, the notion of this centralized core is also morphing and changing, and we're looking at tile designs where we've got replications from 1 to thousands of units, all interconnected, with a network on chip and cache, and having to orchestrate all these things and keep all these things connected. And that's why we're looking to a standard like IP exact to help manage these interconnections.
IP exact's been around for a long time. People have been talking about how this is going to change the industry.
Yeah.
Reality is it was very slow to catch on. What's changed?
What really has changed is the design size and the notion now of these IP blocks. There's no one company that does all these pieces well, right? So you're going to go get the best pieces from the different vendors. And how do you orchestrate and connect those together? And that's the language of interchange that we're talking with IP exact. One additional thing that is new in this space is IP exact just released a new standard through the IEEE in 2022 that is more tightly aligned with system Verilog. Like in the past, when you had system Verilog structs, details on ports, complicated memory maps, you could not replicate those in the IP exact 2009 standard. So there's a cohesion there between the standards that are starting to align that's allowing this to be more useful.
So the standard caught up to what the industry needs, and the industry is finally ready to accept it, right?
Correct.
What's new that's changed when you're working with IP exact? People have some experience with it in the past, but I think it's sort of new when it's coming out now. What's changed here, and what do you have to think about as an engineer?
So as an engineer, when we're manipulating IP exact, it's really the fundamental is XML. So we're moving and massaging XML files on disk, doing different interconnections, deletions, corrections, and that's a lot of data to manage. Even though it's textual, it's not binary format. The files can get very large. The data sets can get very complex. So Arteris has a way of what we call a scratchpad environment of a virtual hierarchy. And the notion is you can do these what if scenarios. You can move blocks around wholesale on thousands of instances and have the tool automatically promote, demote connections, keep track of all the interconnects. And with IP exact, in the standard itself are a set of checks that you can run post restructuring. You would use that even before and during and after RTL. So it's kind of used through the whole process. Now, an IP provider may use the tool to package the IP and deliver it, but in Arteris Magillem, you can actually assemble the whole chip, do the connections, do all the checks, and then generate that structural code to set up the scaffolding for the rest of the design team to either plug their blocks in or incorporate other pieces of IP.
And this gets very complicated as we start getting into some of these advanced chips. And now what you really want to do is say, take a picture of where you are, make sure that everything stays the same, but also now go experiment and play around with what could possibly be done here, right?
Exactly. So in the next slide, we'll kind of see that. So what I've got here is this is a very small subsystem, but this could be considered part of it, maybe a tiled operation. We've got customers with the whole ARM and RISC-V architecture where they've got CPU to kind of manage that, but it's a small tile with some peripherals that has to talk to another block. So this, what I have circled here are 4 or 5 instances, and they were like a subsystem peripherals, and I would like to collect these, and put them in another level of hierarchy. So maybe I'm mid-design cycle. I've got some preliminary place and route data. I've got some preliminary floor plan information that I need to move these and put them in a different way. The physical design team has said, hey, we can't get there from here. So can you move this stuff around for me and give me a new set of code base, right? So what we're going to do here is take these and manipulate these and do that with the virtual hierarchy.
What happens when you get an ECO?
Well, when you get an ECO, then you would just go back to this source. Again, the IP exact is the metadata container for all your source. So it is the one source of truth per se in that instance. So if you edit that, you can automatically edit the rest of the flow.
So you still got to, once you get this done, go through and do the standard stuff, sign off, verify, debug, all the other issues that you would potentially have, right?
Correct.
This just saves you in terms of, we know this is going to work in this way, or we expect it to work in this way. What happens if we make a change over here?
Yeah, correct. Exactly, Ed. Exactly.
What does this look like in a real chip?
So in a real chip, in our virtual hierarchy manipulator, we can take these blocks, move them around graphically, but you can imagine that would be quite tedious, right? For thousands of instances, hundreds of thousands of instances. If you've done any synthesis and you pull up those kind of things in the synthesis tool, you're just looking at something that's really human unreadable. So the idea is here you have the graphical view, but we also can do every operation through an API and specifically through a Python API.
So basically, you're raising the level of abstraction, right?
Correct. So as a designer, here I want to make a core subsystem and shove my RISC-V cores in there. I want to make some peripheral blocks, move those peripherals into that subsystem, have the tool automatically manage this, promote, demote connections, keep track of all that stuff, and then generate a whole new set of RTL for me. So that exactly is what's going on here. We'll open a session, we operate on everything in memory, and then we close that session and write out a whole new project, and we don't destroy the original one.
Where do engineers typically go wrong with this?
Well, engineers go wrong with this in the fact that, oh, I've got this great script. I push a button, boom, I'm done. Verilog comes out, everyone's happy. Now, there is a key piece that if you don't run, it tends to bite you. So in the IP exact standard, there are a set of checks built into the actual reference itself that check for things like bus consistency. It checks for multiple drivers. Do I have ports that are unconnected? We've got extensive connectivity reports and things to help the user before they move to that next stage. So this virtual restructuring happens. You still have to go run the checks, and you got to make sure you have data integrity before you generate that RTL.
But this is a time saver in the design cycle, right? Because it allows you to have that flexibility to say, what's our optimal solution? Let's get there, as opposed to just creating a mediocre chip that does sort of what you want it to do, but not exactly.
Yeah, 100%. And it lets you also spin derivatives quickly. So say I've got one, oh, now I've got this new block of IP. This version of the design is going to have, a greater ALU matrix, or it's going to have additional interface peripherals, wireless versus Bluetooth versus near field communication. You could bring those blocks in and you can configure those parameters and easily plop those in with IP exact and manage all that.
What happens when you get into 2.5D and 3D architectures? Does it change at all?
Not really, in the sense that IP exact is agnostic. So if I'm connecting up, down, sideways, it doesn't really care from that standpoint. Now, what we also are doing to that end is we are trying to bring forward some of these things like standard SDCs, UPF, these kind of things that affect the back end, consider those earlier in the process. Now, that's also an extension to IP exact. However, the 2022 standard has accommodated for that. There are notions of power domains now in IP exact 2022, for instance.
How do all the pieces fit together when you pull all this stuff in? I mean, this is basically evolving over time, right? You don't have a static design that's just going to be here, we've designed it, it's all good. This is going to continue to evolve throughout the design cycle.
Yeah, correct, Ed. Just so maybe I get a new IP drop. Now I've added additional ports. I've added maybe additional register maps. Like, so the memory map changed, right? The architects have said, hey, we need, X amount more memory here. You've got to allocate for it. Now I've got two deltas. We can have the ability to diff and merge this at an IP exact level and take care of that. So the tool will intelligently say, hey, these ports are missing, these are not. Which ones do you want to keep? And it can actually meld those together and help you kind of do configuration management of that part of the design before you, again, generate all the collateral.
Are we keeping up with the complexity in chips? This is one of the big challenges that I'm seeing going on out in the industry these days. Are the tools capable of keeping the design teams in sync with how fast they're supposed to be moving throughout the design cycle?
I think that's still kind of a moving target. We're getting there, but we're getting there in incremental phases. So obviously, as our compute resources get faster, AI comes into the picture and can help with some of this. But we're still seeing this. I don't want to call it an EDA tools arm race, but I feel like it is kind of an arms race between can we get the designer what they need to get their job done. So it is still kind of a push and pull as we move forward.
Tim Schneider, thanks for a great explanation.
Thank you.